Okay, chapter 10 is probability, and the first section is sample spaces and probability. All right, so a sample space of an experiment is all of the possible outcomes. Okay, so let's say you flip a coin 3 times. There's a bunch of different things that could happen. The sample space is all of those, a list of all of those different things. Okay, so let's think through the sample space. So if we're flipping a coin, 2 things can happen with each toss, right? Heads or tails. So let's see, we could get heads 3 times in a row when we toss the coin 3 times. Or we could get 2 heads and 1 tail, and there's a couple ways that could shake out. So it could be you get the tail on the 3rd toss, or you could get it on the 2nd toss, or on the 1st one. Okay, or we could get 1 head and 2 tails, so that could work out like this. Or we could get the heads on the 2nd toss, or on the 3rd one. Or we could get all tails. And there's only one way that can happen. Okay, so now I've got a list. Hopefully I didn't miss any. I made a list of all of the possible outcomes, and this is the sample space. So there's my sample space. The number of possible outcomes, well, each one of these rows is a possible outcome. Okay, so we just have to count up those rows. Let's see, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 possible outcomes. Okay, so if you've got a relatively small amount of outcomes, then it would make sense to make a sample space and just count them up. But these sample spaces can get large very quickly. Okay, so let's look at something called the fundamental counting principle. So that says that the number of options in category 1 times the number of options in category 2 is going to be equal to the total number of possible outcomes. Okay, and that's a little confusing, but it's actually pretty simple if you see it in action in an example. So let's look at this example here. Skeletor has 3 hats, 5 pairs of pants, and 7 shirts. How many possible outfits does he have? So let's assume he's going to, pull 1 hat, 1 pair of pants, and 1 shirt to make an outfit. So I'm just thinking about the different categories here. And I said category 1 times category 2, but you could have more than 2 categories for the fundamental accounting principle like we do here. Okay? So I've got my hats category and the pants category and the shirts category. Okay, and 3 possible hats to choose from, 5 pairs of pants, and 7 shirts. So to figure out the total number of outfits, all we have to do is multiply those 3 numbers together. Okay, so then I'll have 3 times 5 times 7 comes out to 105, and that's how many outfits. Okay, you could make a big chart. You could assign different colors to the different clothing items and make this big sample space, but it would take a while because there's a lot of different combinations there. Okay. All right, so we could have actually used the fundamental counting principle on that last problem. If you think about it here, we've got our first roll, our second roll, and our third roll. And each time, 2 things can happen. So when you multiply those together, 2 times 2 times 2 is 8. So that's the fundamental accounting principle used here. Okay. All right. So got another problem here. Beastman rolls 2 number cubes. Hey, there's number cubes, also known as dice. But we're calling them number cubes because if we say dice, there are dice that have more than 6 sides, right? So how many possible outcomes are there? So there's our first number cube and our second one. And I'm just thinking, okay, on the first die, 6 things can happen. Same thing on the second one. And then so I multiply them together, and there are 36 possible outcomes when rolling 2 number cubes like that. Okay. Okay, let's look at probability on the next page. So the probability of an event occurring is going to be a fraction. It's going to be equal to a fraction where the numerator is the number of favorable outcomes. And the denominator would be the number of total outcomes. Okay, so I usually just say favorable over total for short. But that's what I mean by that. Okay, so, you know, the probability of rolling a 2 on a number cube, well, that's 1 out of 6 things that can happen. So the probability would be 1 over 6. The one favorable roll would be a 2. And then the total outcomes would be 6. Okay? All right, so let's talk about probability. If something is impossible, then it's going to have a probability of 0. 0, it's not happening, right? And if it's certain, has a 100% chance of happening, but the probability would be 1, okay? And if you think about, so something is going to happen half the time would be right in the middle of that number line. So let's think about flipping a coin, right? It's going to come up heads, has a probability of coming up heads 1 out of every 2 times. It's 1 favorable outcome out of 2 total. So it's 50% and comes right in the middle, right? So this would be 0%. You can also write probabilities as percentages because you can write any fraction as a percentage. Okay, and then, you know, there's other places in between on that number line. But okay, so let's look at some example. Orko rolls 2 number cubes. Find the probability that the sum is 7. Okay, so anytime we're rolling 2 number cubes, the total amount of outcomes, we did that example on the last page. You know, we did, 6 things could happen on the first number cube and 6 on the second. So the total is always going to be 36 for rolling 2 dice. So the same thing, just made that's number cubes on the next problem as well. Okay, so then a lot of the work's going to come from figuring out the number of favorable outcomes. Okay, so here I'm going to make a little chart, and I'm just going to start to brainstorm the different ways that you could roll a 7 with two dice. So you could roll a 1 and a 6, okay? And that's actually different than rolling a 6 and a 1. Let's say you're rolling them one at a time. You roll a 1 first, then a 6, or you roll a 6 first, then a 1. That's actually a different outcome. A lot of the time to illustrate this, on the problems they say, okay, you have a red number cube and a blue one. Well, you can see it's different rolling a red 1 and a blue 6 as opposed to a red 6 and a blue 1. Okay, so I can get a 7 like that, but we could also do this with a 2 and a 5 or a 5 and a 2. I could do 3, 4, or 4, 3, and that's it, right? Those are all of the different ways. So then I'm just counting them up. 1, 2, 3, 4, 5, 6. That's 6 out of 36. Okay, so that's my probability, but you'd want to reduce this. So 6 goes into 6 and 36, so 1/6. And you could change that into a percentage as well by putting it into a calculator, right? So let's see, 1/6. 1 divided by 6 is that, and then as a decimal, and move as a percentage, move the decimal 2 spots over. So this would be 16.6% with that last 6 repeating. Okay, most of the time I'm going to write mine as reduced fractions, but just to show you, you could go either way. All right, and then find the probability that the sum is 4. So let's think through our favorable outcomes here. 1 and 3, 3 and 1. 2 and 2. There's only one way to get 4s. You have to get 4s using doubles. You have to get 2 on both those. So you can't swap those and have it be a different outcome because it's the same 2 numbers. Okay, so there are 3 favorable outcomes. And then if I reduce this, I can divide by 3. And I'm going to get 1/12 then. Okay. All right. Let's look at the next problem. All right, Tila randomly selects a piece of fruit from the pictured bag of oranges and lemons. So let's, we can see into the bag, but let's pretend Tila can't see in there and is just going to pick out a piece of fruit, and they're all kind of the same shape, lemons and oranges. So we want to find the probability, first off, that she's going to select an orange. So if you count up the oranges, 1, 2, 3, 4, there's 4 oranges in the bag. And then there are 6 total pieces of fruit. So we got 4/6, or 2/3, or that'd be about 67, roughly 67%. Okay. Find the probability that she selects a lemon. So going back to the same bag, well, there's 2 lemons, and there are 6 pieces of fruit, so that would be a 1/3 probability, or roughly 33%. Okay. All right, next page. Let's look at geometric probability. So geometric probability is very similar, but we're dealing with areas. It could technically be with volumes or something like that, but usually it's areas we're looking at. So it's going to be the area of the favorable region over the area of the total region. Okay, so looking at this problem, let's see. When randomly selecting a point within a rectangle, find the probability that the point is within the shaded region. Okay, so in other words, let's say this is a weird dartboard, and we're going to throw a dart. It's going to land somewhere within the rectangle. Okay, so you're good enough at darts to hit the dartboard every time, but you're bad enough that your shot is totally random within the rectangle. So we want to find the probability that we're going to hit the shaded part. So I'm thinking my probability here, I need to do favorable over total, right? So the favorable region is the shaded part. The total region is the whole rectangle. So I'm just going to draw a little picture of that. That's my total region, the rectangle. So I'm going to find the area of that rectangle. But let's come up with a plan for finding the area of the shaded region. The shaded region is the favorable one. Well, the shaded region is a rectangle with a triangle cut out of it. So that's my plan there. Okay? So then you have to know a little bit about areas of figures. Hopefully finding areas of rectangles is pretty straightforward. You just do base times height. So that's going to be 40 for the area of the rectangle. Okay? And then for the triangle, for triangles, the area is going to be 1/2 base times height. Right? So I'm going to do 1/2 of 3 times 2. Okay? So let's see. That's going to be 1/2 of 6. 1/2 of 6 is 3. All right, so then I've got 37 over 40. Okay, and that's reduced already. Or you could make that into a percentage. 37, I've got 37 out of 40 on a test. That'd be 92.5%. Either way is fine there. Okay. All right. So what we've been talking about so far is theoretical probability. So that's going to be based on what is likely to happen. Okay, so flipping a coin, we're expecting half of the time to get heads, half the time to get tails. If you actually flip a coin 4 times, it's very it might not shake out like that, right? You might get 3 heads or 4 heads or whatever, right? So what actually happens is experimental probability. So this is based on actual trials. Okay, so I'll show you what I mean with this example to try to show you the difference between theoretical probability and experimental. We're almost always going to be using theoretical probability, but once in a while it might be experimental. Okay, so Evil Lynn flips a coin 5 times, and this is what happens. She gets heads the first 4 times and then tails the last time. Okay, for the 6th toss, find the theoretical probability that it comes up tails. Well, theoretically, it doesn't matter what has happened on previous tosses. The probability of this coming up tails is going to be 1/2, right? You can assume on every coin toss, it's half the time it'll come up tails, half the time it'll come up heads. That is theoretically, okay? But the experiment is the same question. Now we want the probability that this is going to come up tails, but this is experimental, okay? So let's say Evelyn is an alien and comes from a world where there are no coins. And so all she has to go on is what has already happened. Well, up here we can see that tails happened 1 out of 5 tosses. So the experimental probability is just based on what's already happened. So experimentally, we think tails is going to come up 1/5 out of the time based on what has already happened, okay? So, maybe it's a weighted coin or something, and it's rigged to come up heads more often than tails. That could happen. So that's where experimental probability comes in. But theoretically, it's 1/2. Okay. Hopefully that is clear there. All right, that's it for this section, and I'll see you next time.